And it's now my pleasure to introduce our second speaker for today, Yichao Tian from Université de Strasbourg, who will speak about rigidity of conjugate self-dual Galois representations.
Okay, thank you very much for the invitation. It's a great pleasure to be here. Yeah. Okay, so this is the plan of talk. The whole talk is based on Appendix E of my joint paper with Yifeng Liu, Liang Xiao, Wei Zhang, and Xinwen Zhu on the Beilinson block-Carter conjecture for ranking step of motifs. You can find the paper in archive. Here is information. Okay, in this talk, I will just start with some examples in dimension 2 and explain what we mean by rigidity in the title. And then I will explain the minimally ramified deformations of conjugate self-dual representations in arbitrary dimension. And then I will state my main result on the rigidity of Galois representations coming from conjugate self-dual regular algebraic Caspita automorphic representation of GLN over FCM view. And at last, I will give an application of this rigidity to prove an R equals T theorem for almost all L. Okay, so let me start with examples. Here is my notation. I start with a periodic local field F, and FQ is its residual field, and gamma F will be its absolute Galois group. And the O will be the ring of integers of finite extension of QL with L different from T. So this O will be the coefficient ring of all the Galois representation. K will be residual field of O, and CO is the category of Noetherian local complete O algebra with this residual field K. So I consider a residual Galois representation of this local field F with value in K, a two-dimensional Galois representation, and I'm interested to study its liftings, or it's also called frame deformations of row bar to an object R of CO. Okay. To explain what is rigidity, I have to explain what do we mean by a minimally ramified deformation row. So a deformation row is called minimally ramified if it has the same ramification type of row bar. It's just a very vague definition. For instance, if row bar is unramified, then minimally ramified means that row itself is also unramified. Okay. The interest of minimally ramified deformation is that the frame deformation run that classifies minimally ramified deformations of row bar is actually formally smooth over O. Then this gives great advantage to study the Galois deformation theory for such representations. Okay. A later question is, when are all the deformations of row bar minimally ramified? So this is supposed to be the simple case of deformations of row bar. Okay, so here. To answer this question, let me remind you some preliminaries on the Tame inertia group. So let IF be the inertia subgroup of the Galois group of F, and IFL be the maximal subgroup of inertia with pro order prime to L. Here are two important observations. The first one is, since this IFL has pro order prime to L, and the kernel of GL to R to GL to K has pro order of L power. So when the restriction of row bar to IFL does not deform at all. So in particular, this means that if the restriction of row bar to this IFL is trivial, then so is the restriction of row for any deformation of row bar. Okay. A second thing is the quotient of the Galois group by this prime to L part of the inertia group is quite simple. Actually, it's topologically generated by two elements. One is called sigma, which is the topological generator for the IF quotient by IFL. So it's a canonical isomorphic to ZL fixed by 1. And this PQ is a list of arithmetic probabilities. And we have this relation sigma Q, PQ sigma CQ inverse equals to sigma to the Q. So to define a representation of gamma, this Tame quotient gamma ft, it suffices to specify its image of sigma and PQ. Okay, so let's first consider the unramified case. Assume the rho bar is unramified and alpha bar, beta bar be the generalized eigenvalues of the rho bar PQ, which is a list of arithmetic probabilities. Then if L does not divide Q minus 1 and the quotient, the ratio of alpha bar, beta bar is not equal to QQ minus 1, then all the deformations of rho bar are unramified. You can check this very easily by direct computation. So hence it's minimally ramified. Okay, if one of these two conditions is not satisfied, then we will get non-minimally ramified deformation. For instance, if L divides Q minus 1, then it's possible to get tamely ramified deformation rho of rho bar to O, such that its image of sigma has this form. Theta L, diagonal matrix, the theta L inverse. Here, theta L is the primitive Lth root of unity. So such a rho is not minimally ramified. And also if alpha, the quotient of alpha bar, beta bar is equal to Q or Q minus 1, it's also possible to get a deformation rho to O with the image of sigma given by a matrix of this form. So it's unipotent matrix, 1 var pi and 0, 1. So var pi is a uniformizer. Okay, such a rho is also not minimally ramified. Okay, in the ramified case, we have similar picture. So assume that the rho bar restricted to IFL is trivial, but rho bar sigma is non-trivial. Then this rho bar has to be of some L power order, so it must be unipotent. It's conjugate to this standard unipotent matrix. Then as long as L does not divide Q squared minus 1, then all the deformations of rho bar also satisfy the same condition. Hence, it's also minimally ramified. And if rho bar restrict to IFL is non-trivial, then also as long as this congruence condition is satisfied, L does not divide Q squared minus 1, then all the deformations of rho bar are still minimally ramified. Okay, you can find these two claims in Jack Shorten's paper, local deformation range for GL2 and for the Mesa conjecture when L different from P. So there are very detailed computations there to give you this result. Okay, so in summary, if L does not divide Q squared minus 1, then rho bar admits non-minimal ramified deformation if and only if rho bar is unramified with the ratio of Frobenius given by Q or Q minus 1. So this is the consequence. Okay, so remember that, then we can talk about rigidity of residual Galois representation of elliptic curve. So let A be an elliptic curve defined over Q with good reduction outside finite set of places S. For each prime L, we have the Galois representation on the L torsion points of A. So you have this rho bar L with value in GL2 FL. And we say that this rho bar L is rigid with respect to this finite size S. If L is not in S, and for every prime P in S, all the deformations of the restriction of the residual Galois representation rho bar to the local Galois group of QP are minimally ramified. Okay, so this is the meaning of rigidity in our sense. Okay, from the previous discussion, actually you can prove easily the following theorem. For all but finitely many primes L, this residual Galois representation rho bar L is rigid with respect to S. Okay, so here is a sketch of proof. Essentially, one needs to show that, okay, by the previous discussion on the minimally ramified deformation, one needs to show that the following three conditions only exclude finitely many primes L. The first condition is L does not divide P times P squared minus 1 for all P in S. So this clearly excludes only finitely many primes L. And the second condition is if P is a prime where A has good reduction, then we require that the ratio of the two Frobenius eigenvalues, alpha P, beta P, different from P minus 1 modulo L. This is equivalent to saying that the Frobenius trace, which is usually called AP, is different from plus minus P plus 1 modulo L. Okay, this also only excludes finitely many primes L because you have the weight bound on the AP, or equivalently, you have the Frobenius eigenvalues are just the P weight numbers of weight 1. So in characteristic 0, this cannot be true. So that only excludes finitely many L. Okay, the third condition is that if P in S is a prime where A has multiplicative reduction, so in characteristic 0, the Galois representation on the IR dictate module has non-trivial monotony. And here we even require that we need the residual Galois representation rho L bar is also ramified at P. So which means that rho L bar has also non-trivial monotony as well. And by Tate's uniformization, then it's easy to see that such a condition is equivalent to saying that the periodic valuation of the J invariant of A is not divisible by L. So this is also excludes only finitely many primes L. Okay, so this proves our theorem. And the aim of this talk is actually to generalize this kind of phenomenon to residual Galois representations coming from conjugate self-dual representations, conjugate self-dual automorphic representation of GLN over F CN field. Okay, so in order to do that, we have to first we'll define the notion of minimally ramified deformations in a higher dimension case. So let me first consider the unpolarized case. So let rho bar be a Galois representation of the absolute Galois group of F to GLNK. And in 2008, Clozel, Harris, Taylor gave a definition of minimally ramified deformation for such a n-dimensional residual Galois representation. Okay, their idea is to first consider the case where the restriction of rho bar to IFL is trivial, then as in the case of dimension 2, any deformation rho of rho bar satisfies the same condition. So such a deformation is determined by the image of two elements, sigma and CQ, subject to the following relation. And we note that rho bar sigma has to be unipotent. So since any element of our power order in GLNK is unipotent, so this has to be unipotent. Then we define rho to be minimally ramified if the image of sigma is unipotent of the same Jordan type as sigma bar of rho bar sigma. Okay, so in general, the image rho sigma can have different Jordan type as rho bar sigma, because the different Jordan type can degenerate. So, But if this does not happen, then we say that rho is minimally ramified. And the general case is reduced to this case by considering tau as a typical component of rho bar for each irreducible tau, which is irreducible representation of IFL to GLDK with D less equal than N. Okay, so this is the rough idea of the definition of minimally ramified deformation in the unpolarized case. Okay, the result is that when L is at least N, then the minimally ramified frame deformation problem of rho bar is actually represented by an object called R rho bar minimal in the category CO, which is formally smooth over O of relative dimension n square. Okay, so here, since we consider frame deformations, there are some freedom coming from the frame. So you should consider the deformation stack as dimension 0 because you have to quotient out by the automorphism of coming from the conjugation of GLN. Okay. Polarized case, and now let me discuss the notion of minimally ramified deformation in the case of conjugate self-dual representation. First of all, let me record the following group scheme, curly Gn. So this is a group scheme over Z, defined as a semi-direct product of GLN cross Gn with group of order 2, which has elements 1 and C. So C squared equals to 1, and the action of the conjugate action of C on such a pair G mu is given by mu times the transpose inverse of G and mu. And let nu be the character whose restriction to the connect component is given by the lateral projection, and its image of C is given is -1. Then if F over F plus is the quadratic extension of fields, and chi is the character of gamma F plus with value in O cross, a conjugate self-dual Galois representation over F with coefficients in an object R of CO and its diminutive character chi is defined to be a continuous homomorphism R from the Galois group of F plus to this curly Gn with value in R, and such that the inverse image of the connected part of this group scheme is given exactly by gamma F, and you get the fixed continuous character chi. Okay, so such a definition seems to be a little weird, but actually this gives the user notion of conjugate self-dual representations of gamma F in the following way. So if you fix an element gamma, which is in gamma F plus, but not in gamma F, then giving a conjugate self-dual representation R in the above sense is equivalent to giving a pair rho A, where rho is a continuous homomorphism from gamma F to GLN R, and A is a matrix in GLN R, such that rho gamma equals to A times chi rho dual A inverse. And this A also satisfies the condition that A times transpose inverse of A equals to minus chi gamma inverse times rho gamma square. Okay, so here rho gamma is the conjugate, is the twist of rho by this element gamma. This is reasonable because gamma F is the normal subgroup in gamma F plus of order 2, and here is a rho check means the conjugate representation of rho. So, so for instance, if such an element gamma has also order 2, then you see this chi gamma has to be +1 or -1, and the rho gamma square has to be identity. So this equation just means that the matrix A is symplectic or orthogonal. Okay, so and the first identity means that you have a perfect parent in the above sense with the similitude character chi, and we consider the deformation problem, which sends an object R in this category CO to the liftings of R bar with the same similitude character chi as well. And by the general theory of Galois deformation, you know that such a functor is representable by the object in CO. So let me call it R local R bar. And then you can show that this local Galois deformation ring is a reduced complete local intersection, a local complete intersection and flat O algebra of pure relative dimension n square. And moreover, you can, if you suppose that L is at least n, then there is a good notion of minimally ramified deformation for this deformation problem. And the subfunctor that classifies minimally ramified deformations of bar is actually represented by a quotient of this local Galois deformation ring called R bar minimal. And this minimally ramified deformation ring is also formally smooth of relative dimension n square over O. Okay, so it's exactly the same dimension as in the unpolarized case, as Clauzel, Harris, Taylor show. And in particular, this spectrum of R minimal is an irreducible component of the whole spectrum of local deformation ring. Okay. Okay, the basic idea is the same as Clauzel, as the case of Clauzel, Harris, Taylor. So you consider first the case when R bar restrict to the prime to L part of the inertia is trivial. And for instance, if F over F plus is unramified, then lifting R of R bar is determined by its image of these two elements, PQ and sigma. So let's say it's of this R PQ is given by B minus chi PQ C, and the image of sigma is given by a matrix A and together with this image of character chi. And by the relation between the sigma and the PQ, you get a relation on these two matrices. B transpose inverse of A times B inverse equals to A to the power of Q. And then most of part of the first statement will follow from this description. And to define the notion of minimally ramified deformations, you suppose first of all L is at least n, then you can write the matrix A, which gives the action of sigma as the form of exponential of some nilpotent matrix X. Then the above equation will transform into this so B times transpose of X times B inverse equals to minus Q times X. So this is equation linear in X, and it's much simpler to study than this one. So then we define R to be minimally ramified if X has the same Jordan type as X bar, which is the reduction of X modulo maximum idea. So this is the case when R bar restrict to the prime to L part of inertia is trivial. And in the general case, you can also consider the tau isotypic component for each irreducible representation of IFL to some some GL and D. Okay, then you can reduce to the previous case, but actually this is most the technical part. This reduction is quite technical, and because the reason is that there is this duality between your Galois representation and it's traced by element gamma. So this tau associative components are related by duality. It's possible that some tau component is transformed to a larger tau component, or one tau component, associative component, is transformed to is in duality with itself. Then, so this causes some complications. Okay, so anyway, once you do that, you will find you can reduce to the previous case. And here, I will not go into detail, just mention that when f over f plus is ramified, then this reduction, finally, you will need the notion of minimally ramified deformation with value in symplectic or orthogonal groups. Unfortunately, this was studied previously by Brewer in his paper, minimally ramified deformations when L different from P. Okay. Okay, so it's natural to ask the following question. Does there exist a general theory of minimal ramified deformations for representations with value in not necessarily connected reductive group? So in the case of conjugate self-dual representations studied here, it's the first the simplest example of such a non-connected reductive group. Okay. There might be a more general theory of this type. So I don't know. Okay, so this gives you the definition of the minimally ramified deformations in the conjugate self-dual case. And now I can talk about the rigidity. Okay, let me come to the global situation. My f plus is from now on a totally real number field, and f over f plus is a CM extension, a totally imaginary quadratic extension. And I consider so-called regular algebraic and conjugate self-dual Caspito automorphic representation of GL and AF, which means that pi is an irreducible automorphic Caspito representation of GL and AF. And if you compose with complex conjugation of f over f plus, you get the conjugate representation of pi. And so this is what we mean by conjugate self-dual. And then by algebraic, regular algebraic, I mean there exists an algebraic representation VC of GL and F tensor with R, such that the Archimedean component of pi have the same infinitesimal character as VC. Okay. I will denote sigma pi to be the places where this automorphic representation is ramified. Okay. In this setup, we already know that such that if you restrict to the subgroup gamma f, then you get a Euro Galois n-dimensional Galois representation, which is semi-simple and characterized by the local long-length correspondence in this way. So if you restrict to some local Galois group FV, then you take the Frobenius semi-simplification of this guy, you get the local Galois representation attached to this pi V tensor with some character. So it's just a normalization for the local long-length correspondence. Okay. Okay. Now for a final place lambda of E as above, let me denote R bar lambda to be, and with respect to rho pi bar lambda be the residual Galois representation. And just as in the case of elliptic curve, we have the following rigidity conjecture. So let sigma plus be a finite set of places of F plus containing all ramified places for the quadratic extension and also for the automorphic representation itself, then for all but finite many places lambda of E, we conjecture that this Residue Galois representation is first of all absolutely reducible, and this its extension to gamma F bar is rigid for sigma plus, so, which means exactly the same as in the case of elliptic curve. So it means that the characteristic of lambda does not divide V for any V in F sigma plus, and the restriction of this residual Galois representation to this local Galois group admits only minimally ramified deformation. So which that means that the deformations, the local deformations are automatically minimally ramified. So we conjecture this is true for all but finite many lambda of E. Okay, here is our main result in this propose this conjecture. Assume that there exists one long Archimedean place W of F such that the local component of the automorphic representation pi at W is supercuspidal, then the above conjecture is true. So actually, in an earlier version of our paper, we proved this theorem under additional condition that there exists another long Archimedean place of F such that the automorphic representation is Steinberg at this place. But then Toby G told us an argument to remove this hypothesis. So I will explain later what this means. Okay. Okay, so here is a sketch. So actually, for the first condition, the irreducibility condition is quite simple in this case, because we already suppose pi W is supercuspidal, so its corresponding local Galois group is also irreducible. Then by the local global compatibility, it's easy to see that the residual Galois representation restricted to this local Galois group at W is already absolutely irreducible for almost all lambda. Hence, the whole global residual Galois representation is absolutely reducible. So the first part of conjecture is quite verified. But actually, for our purpose, we need something more, something much stronger. So this is the following lemma is due to Toby G. So under the above hypothesis of the theorem, then for all but finite many place lambda of E, not only the residual Galois representation itself, but its restriction to the Galois group of F joined with some primitive else root utility is also absolutely irreducible. Then, okay, so if you familiar with Taylor-Weiss method, you will see that such a condition is critical for application for such a method. This lemma will play a fundamental role in the following discussion. Okay. In step 2, we have to prove the rigidity. Okay. So suppose that there exists some V in sigma plus such that its restriction to the local Galois group admits non-minimally ramified deformation. Then we can deduce a contradiction as follows. Okay, so first of all, this condition, the existence of non-minimally ramified deformations will imply that the local deformation space R, small r bar, vert L, has at least 2 irreducible components. Of course, one of which is always the minimal ramified deformation, and the other guy is given by this non-minimal ramified deformation. Okay, then using some existing modularity lifting theorems, one can actually produce 2 regular algebraic conjugate self-dual automorphic representations, pi 1 and pi 2 of GLNAF with the same weight. Weight means the Archimedean component and level as the original automorphic representation pi such that the attached residual Galois representations are the same. But however, you know that there exists only finitely many such automorphic representations of GL and AF with fixed level and weight. So by strong multiplicity 1, all these automorphic representations have distinct Hecke eigenvalues. Then when you modulo some prime L for prime lambda for lambda sufficiently large, then you can actually distinguish all these different automorphic representations. You cannot do this for infinitely many. So pi is not congruent to any other pi prime modulo such a prime lambda. So this get a contradiction. Okay. So in the last part of my talk, I would like to give you application of such rigidity theorem to prove an R equal to T theorem for almost all primes. Okay, so let F over F plus be still a CM extension as above, but for some technical reason, I suppose that F plus is not equal to Q. Let V be a Hermitian space of dimension n over F of signature. Okay, so I should say this is a Hermitian space for the correct extension F of F plus of signature n minus 1 at one Archimedean place and n0 at other Archimedean places. Okay, G is the unitary group attached to this V, and I also fix an open compact subgroup of this finite idea of G, which is hyperspatial outside a finite set of places sigma plus of F plus. I consider now an automorphic Caspito representation, small pi of G idea of F plus such of level K, and such that its Archimedean component is a discrete series with trivial infinitesimal character. So this corresponds to the constant coefficient for the cohomology of Shimura variety, but also you can consider more general setup. But okay, for simplicity, I will just consider trivial infinitesimal characters here. Okay, our assumption is that we suppose that the standard base change big pi of small pi to F exists, and there exists also a long Archimedean space W of F such that the space change big pi is supercuspidal at this W. So in particular, this implies that the whole base change is a regular algebraic Caspito conjugate self-dual Caspito automorphic representation of GL and AF. And as discussed above, there exists a number field E such that for each finite place lambda of E, we have a conjugate self-dual residual Galois representation, R bar lambda, with value in this curly G K lambda. K lambda is the residual field of E, of the coefficient of field E at this place lambda attached to pi. And since we impose this condition, pi is supercuspidal at some place. By our rigidity theorem, we know that such a residual Galois representation is rigid with respect to sigma plus. Okay, so now I consider the deformation problem on the category of OE lambda, which attached to each object R, the set of equivalents of conjugate self-dual representations of R with similitude character given by this guy, and such that R leaves R bar, and R is unramified outside sigma plus, Euro condition, and at places dividing L, I suppose that our liftings of from the Unramified type with Hodge weights contained in 0, 1, and -1, with Hodge weight exactly equal to 0, 1, and -1. Okay. So in particular, this implies that I suppose L is greater than the N and unramified in F. So the last condition is not actually a condition, but I put it here to emphasize that we put load restrictions on the restriction of R to any local Galois group of V for V in sigma place. Okay. Then such a deformation problem is representable by an object called R sigma plus R bar of this category, COE lambda. So on the other hand, we have the Hecke algebra. So let me define the Hecke algebra set. So let T sigma plus be the abstract spherical Hecke algebra outside sigma plus of G, and we have a homomorphism given by the Hecke eigensystem of our Caspita automorphic representation small pi of G, and I put M lambda to be the maximal idea modulo lambda of this homomorphism. Okay, for each finite set lambda, we can define M lambda in this way. You have also the Shimura variety attached to G of level K, which is in our case n -1 dimensional projective smooth algebraic variety defined over F. And the Hecke algebra, this abstract spherical Hecke algebra acts naturally on this atomic homology of the Shimura variety with coefficient OE lambda, and I take the image generated by this abstract Hecke algebra. Okay, then our R equals T theorem is the following. Under the previous hypothesis on small pi, then for almost all finite places lambda of E, the natural surjection from the deformation ring to the Hecke algebra is actually an isomorphism of finite flat local complete intersection OE lambda algebras. And we also have that the atomic homology of the Shimura variety localized at this maximal idea is concentrated in middle degree. It vanishes for I different from n-1, and we localize this atomic homology at n in degree n-1. It's a finite free module over this Hecke algebra. Okay. The validation statement in the second part of our theorem is essentially due to Cariani-Schulze. So what we do is actually to prove that Cariani-Schulze's condition for the validation of cohomology of middle degree is satisfied for almost all finite place lambda of E. Okay. So this is not very difficult. And another, the novelty of our theorem is that in previous R equal to T theorem, we need to put some restrictions on the ramification of F over F plus, or on the unitary group G. So for instance, we usually suppose that G is quasi-split at any finite place, or F plus is unramified as well. So, but in our theorem, we don't need that. Okay. But on the other hand, from point of view of modularity lifting theorem, such an R equals T theorem is not so useful because for almost all lambda of E, we don't have many deformations of the residue representation R bar. But I think such a statement is useful for other purposes. So in our work, in my work with Yifeng Liu, Liang Wei Zhang, and Xingwen Zhu, we used this result to prove certain level reason results for automorphic representations on unitary groups, and such a level reason result is crucial for our arithmetic applications to Benson-Bloch-Castle conjecture for Rankin-Selberg motifs. And also you can get some variants of this kind of R equals T theorem for instance, for the Shimura side attached to a totally definite unitary group, and you can also consider some deformations with some mild ramification at some fixed places. So the key point is that thanks to the rigidity property, we don't need to bother the ramification coming from at the bad places. Okay. So I think experts in Galois deformation theory can easily get this kind of theorem starting from rigidity theorem. Okay. At last, if you want to know more about how this kind of result is related to the Benson-Bloch conjecture and for Rankin-Selberg motifs, you can take a look at the Yifeng Liu's talk, which is available at YouTube, okay, at this link, or you can just search his name and together with Bloch-Castle, for example, then you can easily find it. Okay, so I think I stop here. Thank you.
Thank you very much, Yichao. Let's thank him. And if you have any questions, please raise your hand. Well, I'll wait for one moment and David?
Oh, okay. Hi.
You literally raised your hand. Good.
The statement in your last slide and the vanishing and the freeness over the Hecke algebra.
Yes.
Would you expect, and can you prove analogous results for other kinds of Shimura varieties, maybe for symplectic Shimura varieties?
I think the same kind of method may apply, but I have to check the rigidity results hold for symplectic groups, so symplectic Galois representation. So that means that we need to dispose of some modularity lifting theorem in order to apply the same kind of a strategy. But I hope so, yeah.
Okay, thank you.
Are there any other questions? If not, let's stop the video and thank Yichao one more time.